Hello, my name is Naya Zarati, and I'll be presenting to you our SBIR topic number N19A-T007, sponsored by the NAVC. The title of my talk is Future of Propulsion and Power Generation Electric Motors. Continuous Solutions is a company that has been created in 2014. We focus on power generation and energy distribution components, as well as motors and drives. We've had several SBIR, STTR awards, and we've been able to secure 2 patents. We're applying for 3 additional patents and more in the pipeline. Right now, we are working on a wide bandgap inverter and motor combinations technology. Some of our key resources, in addition to our technical team, we have partnered with Purdue University as well as Florida State University Center of Advanced Power Systems, and this enables us to test our systems in different environments, and as well as access to high power facilities at the FSU caps. Some previous works that we have going on is medium voltage DC grounding system. Originally, it was funded through the PMS 320, in which it's now geared to transition to PMS 640. We've had traction and technical transition success with the TARDAC contract that we worked on from 2015 to 2019. In addition to that, we've worked on unmanned underwater vehicles with SPAWAR as well as VTOL with NavAir. All of this is the propulsion drivetrain and the drivetrain for the VTOL. The Navy is striving to distribute an order of magnitude increase in electrical power without increasing the system space or weight or reducing efficiency. And this requires more powerful rotating machines to fit within smaller volumes, as the current equipment to accommodate new high power energy and sensor systems are currently under development. The Navy also is seeking to develop technology necessary to support design, construct, and qualification of affordable power-dense electrical rotating machines for shipboard applications. And so what we're striving to do in this project is to have a 50% increase in power density above the state of the art that's currently being used. So in this effort, Continuous Solutions was able to design 2 concepts for a high power density rotating machine and demonstrate the feasibility of the concept in meeting the Navy's needs. We also established that it could be feasible to develop in a useful product for the Navy, as well as ensuring that this concept is going to perform as well as the physical and functional characteristics of our proposed system. So in the beginning, we decided to look at 2 different novel topologies, one being a trapped flux core machine, which is a TFC machine utilizing superconducting material. And then the second one, which is an asymmetric permanent magnet synchronous machine or motor technology. Both of them showed significant improvements in the power density, well over the 50% target in which the Navy requested from us. Based on the phase 1 results, we were able to start a scaled down version of the APMSM. So we've been able to develop a 10 kilowatt scaled version, fabricate it, and we're in the middle of testing and delivering the prototype as a use case. So really the biggest technological development is the genetic algorithm or the multi-objective optimization utilizing evolutionary computing to come up with a topology that basically hits all of the points for power density as well as functionality. The APMSM enables an increase in power density that has a dominant rotational direction. So the asymmetrical, meaning that the magnet structures um, on the in the motor is one directional or favored in one directional. It's projected that the machine is going to be operating at 150 RPM at a power level of 20 megawatts for a propulsion motor. And we are looking at this design to be an air-cooled system. The rotational asymmetry added to proven technology, improves this torque for a dominant direction motor. And again, this design was optimized with evolutionary computing, and we have been able to create a prototype scaled version of this topology. So the development currently, as it stands for our STTR Phase 2 Year 1, is a fully assembled and constructed reduced scale prototype of the APMSM. We are hoping that by the end of the 3 years for Phase 2, we will have achieved a TRL Level 6 for this reduced scale 10 kilowatt. The design and fabrication of this 10 kilowatt prototype was completed in August 2021. We have since began testing the prototype in Purdue's laboratory, as well as beginning the design of an additional reduced scale of 100 kilowatt APMSM as well. These theoretical designs are for the assessment of the full-scale 20 megawatt designs with a conventional material and proven architecture to achieve that 50% improvement of power density over the state of the art. We also have different applications for these reduced scale motors and machines specifically for marine tech applications. We are doing a comparison of the torque density rather than the power density for the reduced scale, since these reduced scale machines are operating at a much higher RPM. So this is an outline of our complete Gantt chart for the Phase 2 base. This Gantt chart is a layout of our 3 prototype developments that are underway. The first one being the 10 kilowatt APMSM prototype development. Prototype 2 is the 100 kilowatt APMSM. And then prototype 3 is the 10 kilowatt static trapped flux core motor, utilizing superconducting material, yttrium, barium, copper oxide. For this chart, and for the way that we develop any prototype, is a series of documentations that are passed between the client and Continuous Solutions. We develop a document on the specifications and requirements. We conduct a requirement review. From the requirement review, we prepare a preliminary design review, which is all of the engineering documentation put together and presented to the client, in this case, the Navy. And in the end, we have a second design review called a critical design review, which happens right before we start the procurement of materials and the manufacturing or prototyping build of the prototype. After we do the completion of the builds of the prototype, then we submit a test plan on how that test plan is going to be qualified against the prototype. And we conduct the testing of that test plan. At the end, we deliver the product with verification and validation based on the test plan. So some of the key features, and we pulled directly from the requirements document based on the full-scale rotating machine that we are building for or towards for the Navy. We also have our prototype rotating machine, which is the scalable version of the full-scale machine. So the requirements are based primarily on the full-scale rotating machine, and we try to scale down to 10 kilowatts and make it an equivalent. So for the power rating, we are getting it to be functional up to 34 megawatts. The input voltage is 60 hertz, 440 VAC, in accordance with mil standard 1399, section 300. The size of the system is not to exceed a certain envelope that increases the state of the art by 50%. The weight of the system is not to exceed 87 tons, and the operational output, it shall be capable of operating at 100% duty cycle for an extended period at varying speeds. And what we've done is taken these requirements and bring them down to the 10 kilowatt scale. So how can we transition this to a naval fleet? After validating the 10 kilowatt, 100 kilowatt prototypes, we believe that this projected power density increase for 50% over the state of the art will provide confidence in the machine design tool that we've created, as well as the scalability. So scaling it up by one order of magnitude, it's possible then, or to infer that we can scale up another order of magnitude and then another one after that. So validating the APMSM topology is very important. In addition to that, we have the trapped flux core machine that is being tested magnetically as well as thermally, as intended in a static machine prototype, to show proof of concept and functionality that the YIBCO, or the yttrium barium copper oxide superconductor material, will be sufficient for a more power dense design. The approval of these specifications, testing, and prototyping are done by the Department of Navy, specifically NAVSEA. And in addition to that, we're looking for advocates to transition this technology in the 10 kilowatt and 100 kilowatt level prototypes for application to potentially smaller scale vessels or applications in other areas where a directionally dominant electric motor would be applicable. And we're also looking for a transition to the DDGX applications for full-scale design of the 20 megawatt electric motor. So if you're interested in continuous solutions, in particularly this project and the other projects we have going on, please come and find me, come talk to me. I will be at the San Diego Navy Conference on February 15th and 16th. And if you are not attending that to meet me in person, please reach out via email or contact me through phone. I really thank you for your time and look forward to speaking to you soon.